So now we consider some application. So we want to prove the Erydian-Stone-Simonovich theorem, which says that if you have a graph with sufficiently large number of vertices, so for given delta positive, and if you have a sufficiently large n, and then G is an n vertex graph with this many edges, then you can find the okay, let's do it from the beginning. Okay. For given H, K bipartite, say, and delta positive, then if n is sufficiently large, then this holds. We have this. So that's the statement of Erydian-Stone-Simonovich. So suppose that we have H, which is K bipartite, and delta is given, and we choose epsilon smaller, sufficiently smaller than delta, and then we make sure that n is, say, n0 is much sufficiently smaller than epsilon, and n is bigger than n0. And assume that you have a graph with this many edges. Then we apply regularity lemma. To G with, say, t being 1 over epsilon, small t. Then we get a epsilon regular partition satisfying P1, PR of G satisfying R1 to R3, and let R be an epsilon delta over 3, say, reduced graph. Let's say delta over 4. Then we apply the proposition 2.1, 6.21. So this proposition. So we know that the average degree of R is inherited from the lower boundary, inherited from the average degree of G. This gives us a bound on the number of edges in R as well. Then from that we can actually show that because epsilon is small enough, then we can actually conclude the number of edges in here is 1 minus 1 over k minus 1 plus delta over 4 times r squared 2. So what do we know? Then by the Turan theorem implies R contains a copy of KK. So here, let's specify a bit more. So we can actually take epsilon be smaller, so that we can invoke the previous embedding lemma. So we say that H has the number of vertices H. Then we make sure that T over 2 to the H. So we can ensure that epsilon is smaller than this. No, not T, delta. Then here, what we get, we get these copies That means in G, we have a corresponding vertex set, V1 to V2 to Vk, say, K of them, so that each part are epsilon delta plus regular. Epsilon regular with the density at least delta. Many times we call this each set as a cluster of this epsilon regular partition, meaning each set. So we have K clusters, and they are all epsilon delta plus regular. And then we can, previously ensure that this 1 over, n0 is so small so that n0 is bigger than t of epsilon times h times 1 over epsilon. Then there are r parts in the regularity partition. So each part has size at least, say, h times 10 epsilon. So each of them has size bigger than, size of h times 10 over epsilon. That means when we have h, it is k partite. So you can partition it into k parts, and each is x1 to x2 to xk. Each part xi is smaller than epsilon times vi. So in the regularity partition, you find the kk, copy of kk in R, which gives us this k cluster. This index could be different, but we can just assume that those indexes are 1 to k. Then now we have a position to invoke the embedding lemma. So by the embedding lemma, we can find the embedding of h into G. So h is the subgraph of G. So this proves that, we have the upper bound on the extremal number of h, so which shows the distance Shimonovich theorem. Another application that we are going to consider is about the Ramsey number. We define the Ramsey number to be, in the undergraduate graph theory, we define that as f h1 and h2. This is the minimum number n such that any two edge coloring with two colors of Kn contains either red H1 or blue H2. So monochromatic copy of H1 or H1 in first color, or monochromatic copy of H2 in the second color. And it's well known, or we actually learned it in undergraduate graph theory, that this exists for any pair H1 and H2. And for general graph, this is exponential in terms of number of vertices here. Let's focus on the case and H1 and H2 are same. For example, we know that R, KD, KD, so for complete graph, it's at least 2 to the d over 2 and at most 4 to the d. We know this. This is what we learned in undergraduate graph theory. So this has d vertices, so this is exponential in d. But Vatar and Rodel and Semoredi, Trotter proved that in 1983 says that if H has maximum degree bounded, while the size of H could be large, then this RHH Ramsey number is only linear in D, in the number of vertices. So if H is a very big cycle with a very large number of vertices, say n vertices, then its Ramsey number is only linear in terms of n. Here, this could be some number depending on this maximum degree. If this is cycle, then delta is 2. In that case, this could be, some constant, which does not change as n grows, which only depend on this delta. Of course, dependency on delta could be big. It could be this large number, but still it is just constant compared to n. And this can be actually proved using regularity lemma. So let delta be the positive number and let h be a graph of maximum degree and most delta. Then we want to prove that there exists a constant which only depending on delta, such that Ramsey number is almost the C times the number of vertices in H. So how do we prove it? As before, we want to apply regularity lemma, and then we get this regularity partition. And we want to find certain parts which are again, complete in the reduced graph, and then we want to embed H into here. So that's roughly our plan. But what graph do we apply regularity lemma? So here, what we do is we take the complete graph and then we consider the coloring. So what we do is we consider the graph which uses only red color. So we consider all the edges with red color and then apply regularity lemma here. If we find some structure like this, then we embed H into red graph. But if there is no such thing, then we can find many pairs which that the non-edges between them are epsilon regular. So once you take the complement, it is epsilon regular. Then you again, epsilon regular with certain lower bound on the density. Then we also embed H here. So that's our plan. So for that, we first consider the Ramsey number on complete graph on delta plus 1 vertices. Be the Ramsey number of k sub t delta plus 1. So this is at most 4 to the delta plus 1, we know. In other words, however you color the edges of kk with the two colors, you can always find the monochromatic k sub t plus delta plus 1. So we take epsilon to be 1 over 2 to the delta plus 1 k. And say t is k plus 1. Then by the regularity lemma, there exists t such that, t as in the regularity lemma. Again, this t is only depending on epsilon and t, and those two numbers are only depending on this delta. So we let C be the 3 times epsilon inverse times t. Which is the function which is only depending on this number delta. So take n to be the, C times the number of vertices in H, which is this. And we want to show that any 2H coloring of Kn contains a monochromatic copy of H. So consider 2H coloring. Of Kn by color red and blue. And let G be a graph, be the graph with red edges. And we apply the regularity lemma. To G with parameter epsilon and t. Then there exists an equitable epsilon regular partition V1 to VR, satisfying R1 to R3 as before. Then what we know, each VI has size at least 2 times epsilon inverse times size of H. Because we have this, and then how many parts we have? R, but R is at most T. So you divide this by T, then that's already 3 epsilon times H. So this lower bound holds. So each part is big enough so that later we can actually apply the embedding lemma. So we consider an epsilon 0 reduced graph. That means, we don't care about the low density. As long as some pair are epsilon regular, we consider the pair, and then we just forget the all non-epsilon regular pair. Then what do you get? So from R3, we know that this is always epsilon regular except epsilon times R square pair. That means this capital R is very dense graph. By R3, we know that the number of edges in R is at least 1 minus epsilon times, let's say, epsilon times R choose 2. And this is bigger than 1 minus 1 over k minus 1 times R choose 2 because of our choice of epsilon. Thus, what do you get? By Turan theorem, R contains a copy of KK. So that means there are K parts, K clusters, so that every pairs are epsilon regular. All of them are epsilon regular. We don't have to worry about the irregular pair. And now, now here, there could be many red edges, then we are good, but there could be not so many red edges, then we are not good. We cannot really invoke the embedding lemma to embed H into the red graph. So now we use now we use this fact of our choice of K being the Ramsey number. We consider the copy of K sub K in R and color IJ of this H in complete graph. Again, by let, if this Bi, Bj has say density in Bi, Bj is at least half, and blue otherwise if the density between them in G is strictly smaller than half. Then, by the definition of K, there is a monochromatic copy of K sub delta plus 1 in this KK. So we assume that by giving the index again, reindexing forms such a monochromatic copy of K sub delta plus 1 in R. If this is red monochromatic, then let's say G prime is G. If this is blue monochromatic, then let's say G prime is the complement of G. Then G prime on this delta vertices. Okay, let's write it this way. So let G prime be the graph in G, which is induced by those delta plus 1 clusters. Then now we want to just show that we can embed H into G prime, because G prime is a monochromatic subgraph of Kn. And for each ij inside of this between 1 and delta prime, we know that Bi and Bj is epsilon regular with the density at least half. Also, H is delta plus 1 partite by the just maximum degree is delta, so it's delta plus 1 colorable. With each part of size and most, the entire number of vertices, which is smaller than epsilon times Bi. So by embedding lemma, we know that the H is inside of G prime, and which is a monochromatic subgraph of Kn. So hence we conclude that there exists a monochromatic copy of H. In this 2H color in Kn. So hence, by the definition of Ramsey number, we have the Ramsey number of H is M of C times H, where C depends only on the delta, the maximum degree. So this proves the theorem. But how large is this C delta? C delta is because we use the regularity lemma, and then we actually multiply this T, which comes from the regularity lemma. So this is actually very large. So this is tower of some polynomial in delta. But I mean, if we use something called dependent random choice, which we don't have time to cover in this class, then we can actually show that this is some constant times delta, log delta. I mean, exponential in constant times log delta, log delta. So we can show that this is, I mean, at most this, a bit more than exponential. And this is only for bounded degree graph, but recently in 2017, Jungbom Lee showed that if H is D degenerate for bounded degree D, bounded number D. Degenerate, I mean, is a weaker condition than bounded maximum degree. Then the Ramsey number of H is at most some constant depending on D times the number of vertices in H. So we have learned regularity lemma, and then show how we can use this to the problem of finding some subgraph in G. And next time we will learn more about the similar approach, but not just finding one subgraph, but we want to find the many subgraphs inside of G. That can be also done with this regularity, and then we see, what kind of application are there for, with that fact.